Are we streaming this, by the way? I forgot to ask. I noticed. Yes. The streaming has already started. Are you doing it via Zoom or externally? Okay. Okay. So while we wait for the other participants to join, if there are more numbers, briefly wanted to check if there are questions, if any. And I'll share my slides shortly. So participants, if any of you have any questions, you can feel free to raise your hand. I don't see any significant question on the Google form from any of you. So I'll wait for 2 more minutes and then I'll start. Dibakar Datta asks, sir, can you please suggest a book for learning about the SAA equation? Well, the SAA equation is applied in a wide range of astrophysical scenarios. I can suggest you can look at, for example, Paddy's book, which covers a wide range of astrophysical processes, and SAA equation is part of it. It must also be there in any standard stellar structure books because that is what it is. It has been widely used for. Yes, that's right. It is by Paddy. I mean the theoretical astrophysics series by Professor T. Padmanabhan. Again, I'll ask all the participants to. Okay. Yeah. So Dibakar again. I think I would strongly suggest getting all of the Paddy's books because they are very nice and concise, and they should be helpful for your teaching as well. Okay, I'll ask all the participants once again to rename yourself to some legible form. For example, I can see a member whose name is star dollar at the rate hash and hash whatever. Please rename yourself to your first name or the name with which you have registered for the summer school or the refresher course. Thank you. Any other question from anyone from whatever was discussed yesterday? Okay. If not, then let us begin for the last lecture of the series. Yes, it works now. Okay, so what we had talked about in the last few lectures, I'll just give a brief recap and then proceed onwards. We had learned about some of the fundamentals of how the electric and magnetic field from a moving charge looks like, and discussed the implication of when the charge is accelerating and charge is moving, how the field changes, etc. We learned how the fact that from a accelerating charge, you have a component of the electromagnetic fields that gives rise to radiation or emission that propagates with distance. And we learned about the fact that if you compute the Poynting flux and you can get the total amount of power going through particular solid angle, how that is related to the charge's velocity and the acceleration. And that is called the Lamar's formula. We then talked about basics of some of the basics of relative angle transformations in special theory of relativity, mostly to understand that if you have emission from a fast moving charge, the emission is beamed in the forward cone along the direction of motion of the charge. And we use these concepts to understand some of the basic properties of emission from a charge that is gyrating around a magnetic field. The special case I talked about was the synchrotron radiation. We can also have cyclotron radiation when the charge's motion is non-relativistic, but I did not discuss it yesterday. So synchrotron is when the charge is highly energetic with a substantial Lorentz factor. It is moving around the magnetic field, perhaps in a helical path, and the fact that it has some acceleration involved, it will emit radiation. So we again learned about what is the expression of the power radiated by the charge, the total power. And then we also saw how we can, well, I did not give you the exact description of the derivation, but how the spectrum from such a charge looks like. If the total power is this from the Lamar's formula, the spectrum or the frequency distribution of that power looks something like this, where it is proportional to the perpendicular component of the magnetic field intercepted by the particle and a function fx which is related to the Bessel's function. Okay, so this is how it looks. We also understood that there's a critical frequency associated with such a charge emission from such a charged particle, and the spectrum peaks at around 0.3 times that critical frequency. So that is the power peak distribution. So if you know the Lorentz or the energy of the charged particle or the Lorentz factor of the charged particle and some measure of the magnetic field, you can more or less identify at which frequency, which characteristic frequency will the particle be emitting the radiation. And that is close to the critical frequency, 1.3 times the critical frequency. We also saw that if the particles are distributed as a power law in energy space, in phase space, how the synchrotron spectrum looks like in that case. So if the particle distribution is a power law with an exponent with the expression given like this, such that the energy distribution of the particle is proportional to e to the power minus p, then if you put that in, so essentially what we do is we take the synchrotron emission of a particle with a given energy E and just integrate over this energy distribution, with which we get this dependence on the frequency. But the total power is proportional to the frequency to the power minus p minus 1.2. So I discussed this, and in actual observations, what we do is we look at the synchrotron emission at different frequencies from the radio telescopes, and we can infer the slope of the radio emission, which gives us a handle on the energy phase-based distribution of the particles at that particular location. And this is a very powerful tool which enables us to understand the characteristics of the emitting region. For example, what is the nature of the particles at that location? What is the age of the particles? We can all do this from understanding the spectral maps. So this is where we had stopped. I hope there are no questions now. If there are any questions, I didn't see any raised hands. But if there are any questions, you can write in the Google form. And I will try to address it at the end of the lecture. All right, so in today's lecture, we would study about one more such radiation process, which is called the Bremsstrahlung emission. Now, in the previous form of radiation, what we learned about was emission from highly relativistic particles. So the relativistic particles are not thermalized, so they are not non-thermal emission. Non-thermal meaning that they are not in thermal equilibrium with the environment, and that is why you cannot ascribe a single temperature to those particles. And this is where the caution that I had presented much earlier, the fact that if you have a brightness temperature, it is naturally assigned to a temperature of the field, but that is not exactly true. Exactly, now you understand. For example, if you take the synchrotron emission and compute the intensity and assign a brightness temperature to it using the Rayleigh-Jeans expression of the black body function, you can get a value of the temperature, but that does not represent any physical temperature of those highly energetic relativistic electrons. That is just an empirical characterization of the intensity distribution. However, if you have emission from a thermal system, then truly that is the brightness temperature that you infer is close to the physical temperature of the system. So yesterday's discussion was more about non-thermal emission. Synchrotron is an example of non-thermal emission. And today we'll learn about something that is closer to the thermal system or thermal emission. So what we will be trying to understand is if we have a stationary ion or a heavier charge and an electron goes past it, the trajectory of the electron would be affected by the fact that there is the ion sitting near it. So if you look at the path of the electron, very far off from the ion, it is coming here with some impact parameter B, and then as it starts interacting with the ions at E, its path will slightly bend. And the fact that its velocity is deviating, even though by a very small amount, means that it is experiencing some sort of acceleration, and that means that it will be emitting energy. Now, for this system, we will assume that the ion is part of a distribution of particles that are thermal in nature. So it is coming from generally ionized medium, where you have both electrons as well as ions because of the nature of the ionization. And then when these electrons interact with those ions, they will emit some energy. And that is the essence of Bremsstrahlung emission. So physical picture is you have a thermal distribution of plasma, ionized plasma, and the electrons and ions are interacting with one another. And the fact that this is electromagnetic interaction, the trajectories of the electrons, so electrons are free electrons, by the way, so they are freely streaming. They're decoupled from the ions, and that's why they are ionized. And the fact that the electrons are interacting and their trajectories are changing, that means that they'll be emitting some radiation. So this is a physical picture. If the following mathematics seem a bit dense to you, so physically you can understand it this way. Now, what we are interested in is understanding the total power and the spectrum of the radiation that will be coming out due to such an interaction. Okay, so to do this, then we go into the quantitative estimates of these things and go into the nitty-gritty details. Again, I must warn you that usually Bremsstrahlung takes me a couple of lectures, at least 3 or 4 lectures, to explain in full detail, because there are certain aspects hidden inside which require a previous set of discussion to elucidate the mathematical foundations of it. I do not have the time for it, so I'll try my best to explain the physics or the physical implications of what we are doing, while also showing you the flavor of the mathematics. For further details, I will refer you to the book by Rybicki. Rybicki has a very fantastic description of Bremsstrahlung, along with others. Longier's book has a more grounded and mathematically sound description of the Bremsstrahlung emission, but Rybicki is also good. Okay, so to approach this problem, what we do is we identify the dipole moment of the system. And the dipole moment of the moving charge d is minus E times R. R is the interaction zone. And what we'll do is we'll perform the Fourier component of the of the dipole moment, or we'll essentially try to identify this d omega. Why we do it? Again, this is exactly what I was saying, that I cannot discuss everything in detail because there is a relation that one can prove, which is the spectrum of the power emitted is proportional to the Fourier transform of the electric field. So if you forget everything on this slide now and just look at the right hand corner. Yes, Subrata Sarangi, please keep your hand raised on the question. I'll come back to you very shortly. So just focus on the right hand corner over here. I should have placed a box here. I want to do that. So what I wanted to say was that this part of the derivation is something that I'm not showing, but you'll have to take my word for it. So the total power emitted per unit, so total energy per unit area per unit frequency. So, oh, sorry, not energy, this is power, dw is the power. Per unit area per unit frequency, which is essentially the spectrum emitted, is proportional to the square of the magnitude of the Fourier component of the electric field. Now, the derivation of this takes a bit of time, and it's there in Ribicki Enlightenment, so I'll not go into it, but I'll assume that this exists. So then what we have to do is we have to find out the electric field, and to find the electric field, what we do is or the Fourier component of the electric field, and the electric field of the dipoles will be related to this of a dipole system can be expressed in this way. Again, a simple derivation using multipole expansion, but again, I don't have time to do that. So you have to take my word for it that if you have a dipole moment, and if the dipole moment is changing with time, then the electric or the radiative part of that electric field of that dipole moment is represented in this way, which is n cross d double dot divided by c square r naught. R naught is the distance from the dipole location to the observing point. N cap is the unit vector from the dipole towards the observer, and d double dot is the acceleration or double derivative of the time of the dipole moment. For example, if the dipole moment is this and it is changing with time, d double dot gives you the double time derivative of this dipole moment. And if you take a Fourier transform of this field of this expression, you get something like this. Okay. So if you get, for example, now the Fourier transform of the dipole moment, you recover the Fourier transform of the electric field, and with that information, you can find the power emitted per unit frequency, and per unit solid angle as well. So dw d omega, the capital omega. So this gives us a spectrum. So to identify the spectrum that is coming out of it, that is what we need essentially, the spectrum as well as the total power. So to identify the spectrum, we have to find the variation of the Fourier component of the dipole moment. So in that context, what we do is we identify the dipole moment and take a Fourier transform of it. Now, dipole moment, as you can understand, is given by the p dot. So the Fourier transform of the dipole moment is given in this way. We take the acceleration vector and then do the standard Fourier integrals. Now what is important about the physical understanding of this is how we can define the acceleration vector. Okay, so in this particular scenario, if you just work out the different velocity components, you can have two components of the acceleration vector. One, acceleration parallel to the initial direction of the electron, and the other, acceleration perpendicular to the initial direction of the electron. So all of this are related to the time t. So let's take that time t equals 0 is the point of the closest approach. So you can see that the parallel component of the acceleration vector starts off from a minus infinity, goes to minus infinity, and then goes to t equals to plus infinity. So there's a change in sign. So it's flipped sign. So from the point of view of the electron, this is just almost like a short spike with a sinusoidal component. And the total integral of this component would be 0, or integral over time. That is why we can sort of neglect the parallel component of this in the integral over here. The perpendicular component, on the other hand, just depends on time in this way, which is 1 by b squared by plus v squared t squared to the power 3 by 2. This will not cancel out. So just from a physical perspective, I'll again go to the more detailed mathematical derivation of this in the next slide from Longest book. But this is a very intuitive physical argument, and this comes from Rybicki, that for computing the Fourier transform of the dipole moment, we neglect the parallel component of the acceleration field, and we only retain the perpendicular component of the acceleration field. So we are all set now. We have the acceleration. We can compute the Fourier transform of the dipole moment. With this, we can compute the spectrum of the Bremsstrahlung for a single electron. Now, here is a more detailed derivation, but before I go there, I saw a raised hand by Dr. Sarangi. Do you want to ask any question if you have any? Subhadra Sarangi, if you have any question, can you please respond? Okay, I don't see the raised hand, so I guess it was done in error. Okay. Yes, Dr. Sarangi, please unmute yourself and ask the question.
Yeah, okay. I hope you are able to now. I was unable to unmute at that.
Yeah, that's okay. Yes,
Yeah.
Well, we can hear you now.
Yeah. I was just missed your definition of that capital in that definition of dipole.
Okay.
So is it the position vector of
It is
the
a
electron with
position
respect
vector
to
from the
ion?
point of, it is a position vector from the point of the ion to the electron.
Yeah. Okay. That's all. I just need to.
Okay.
Yeah. So that is as R changes, D will also change. So that's how it is.
Yeah, that's right.
Thank
That's
you.
right.
Yeah. Okay.
Okay. Thank you. Okay. So then this is the more formal definition of how you can compute in a more mathematically sound way without taking any approximation. So we will not drop the parallel component of the acceleration field. So we have the full-fledged acceleration vector here. We'll take a Fourier transform, and A omega is the Fourier transform of the acceleration vector. Now you have both components, a perpendicular, a parallel. Again, I do not expect you to follow the mathematics, okay? And again, just listening to this does not really help you. You have to really work it out by hand to absorb it in your mind. But what I wanted to share was the nuances. So even by doing the simple approximation, the result we get, we can also derive it more formally using the mathematical principles. And that's why I wanted to impress upon you that the approximations we made are not that bad. So you can take the full expressions of the A perpendicular and A parallel and then compute the Fourier transforms. They give you some expressions in terms of the Bessel functions. The total energy now is, without neglecting anything, is A perpendicular omega squared and A parallel omega squared. Again, the basic fact is, there is a typo here. And I will, this P3 is wrong. So ignore this one now. The expression would be very similar as here. 8 pi omega 4 by c cube. Okay. So, but essentially, what I wanted to impress was this dWd omega, which is the spectrum, is proportional to the square of the A perpendicular and A parallel square of the Fourier transforms. Now, there is something interesting when you actually consider the full expressions of A perpendicular and A parallel. So K0 looks something like this, and K1 looks something like this. And X is the ratio of the omega over tau. So essentially, what you will find out that if you collect all the terms, the contribution from for this factor, well, omega tau, what tau is the characteristic time scale of the interaction. If this is less than 1, then you have the spectrum here, and if this is greater than 1, then you have zero contribution. And the parallel component satisfies this. So the parallel component, if you work out everything, will have very little or almost tending to zero contribution to the spectrum. And this is true for the perpendicular component. Okay? So essentially, whatever we approximated earlier is true. Okay, so this was the expression of the emission for a single particle. Now, what we would like to do is, if you have a distribution of ions and if you have a distribution of electrons, how would the emission look like? So essentially, what you will have for a single ion, if you have a distribution of electrons all moving parallel, for example, and interacting with that ion, you can think of concentric circles and then small areas along these concentric circles to understand the total number of electrons interacting with that ion in this concentric circle. So you know what is the expression for a single such interaction. Now you all have to do is find out the total such interaction. So what you do is you take the expression for a single particle with a given input parameter. So the total number of ions is, so for this is for a single ion, and for to find for all the ions we just multiplied by Ni. Ni is the ion density. So this is per unit volume. So what we learned in the previous slide was the emission due to a single ion and a single electron. Now assume from the ion's point of view, there are many such electrons going and interacting, almost like a beam of electrons that are flowing the same direction and interacting with that ion. So we have to just find out the total number of electrons, and with that, to do that, we consider this integral over here. We take a cylinder with concentric circles and then integrate along the radius of the cylinder. We start off from a minimum impact parameter, and I'll come again why this is the case, and integrate to infinity all the way up to a maximum value, not to infinity exactly, but to a maximum value. And do I define the expression of tau? Yeah. Okay. Yes. Sorry, I was just checking something where a different thing. So again, if we can define the characteristic interaction time scale omega tau to be less than one, then one can integrate. So again, all we do is take the previous example and the previous case of the total emission that we get for a single particle, plug in that form over here, and then we just perform the simple integral. So this gives you the total energy per unit frequency, per unit volume, per unit time of a beam of electrons interacting with the distribution of ions. Now, what is important to note here is the fact that you have this in logarithm, a ratio of the maximum impact parameter and the minimum impact parameter. Okay. So the upper limit is when you have the maximum impact parameter close to the velocity divided by the frequency. So this is the interaction time scale, or tau is interaction time scale over which this is happening. And the upper limit comes from the fact that B max is V by omega. Okay, so essentially what the frequency at which you're observing, yeah, that gives you a characteristic time. So velocity divided by that gives you the characteristic length scale. So this gives so B max comes straightforward from this expression, but the lower limit is something a bit more tricky. So there are two cases of the lower limit. One is a classical case where you say compare the kinetic energy of the particle and the electrostatic energy of the ion and the minimum energy of the electron and the ion. When these are comparable, you again get a characteristic a minimum impact parameter, which is BC minimum in this way. And then again, there is a quantum mechanical expression of it, which comes from the quantum and the uncertainty principle, for example. You have a limit on the delta x based on the fact that you know the momentum of the particle, and you have the h bar. So with these two, you can have a wide range, a certain range of impact parameters based on the energy of the particle and the frequency at which you're observing things. So this becomes a bit tricky to how to calculate it, and we have standard charts that have been formulated. There is a very nice review on Bremsstrahlung by Novikov and Thorn. So I would always suggest that people who are actually working on Bremsstrahlung emission, you can learn about the basics from the textbooks like Rybicki, Lightman, and Longueur. But the review by Novikov and Thorne gives you the more practical application-based description of Bremsstrahlung, with all the given charts and tables of how you can compute these Gaunt factors over here. So essentially, what we say is that this logarithmic stuff in the after that we get out of the integral is called the Gaunt factor, and the total power in such a system is proportional to the square or Ni times Ni. So if you have Ni is the number density of the electrons and Ni the number density of the ions, essentially in order of magnitude you can see that it is proportional almost to the square of the total number density of the particles there. So this is important because if you this is square of the n of the number density. If your number density increases by 2, then the emission increases by a factor of 4. This is very important to note. And then you have a Gaunt factor. What is important to note, a Gaunt factor is usually a logarithmic term. So even if you have made small approximations in the expressions of B max and B minimum, the error would be negligible because it would be sort of suppressed by the logarithmic nature of the Gaunt factor. But to accurately evaluate the Gaunt factor, what we do is use lookup tables, for example, as given in Novikov and Thorne. We calculate the frequency. We first identify the frequency at which we want to find the emission, because this is a spectrum. Then we also find the velocity of the charge, because here for this we have just assumed that there's a distribution of this is spatial distribution of the ions and electrons, but all the electrons are moving with the same velocity. So what we do is h nu by half mv square on the y-axis, and this is a ratio of the kinetic energy of the electrons with respect to the Rydberg energy. Rydberg energy is gives you a measure of the electrostatic potential energy. So half mv square divided by the Rydberg energy. Once you can find this out, then you can find out which form of the Gaunt factor you would be using. Okay. Okay, so I see that I did not discuss the thermal plasmas here. So just to give you again an example of what is the next step. So what we have done so far is assume that all the electrons are moving with the same velocity. Now, but that is, and all the ions are also static, but that is not the case in a realistic system. So this is where the thermal nature of the particle of the matter distribution has to be considered. That if it's a thermal and non-relativistic system, the particle distribution would be in the form of a Maxwell-Boltzmann distribution. So what we do at that point is integrate over the velocity space of the electrons using the Maxwell-Boltzmann function, and that gives you a typical temperature. So you then replace the y-axis with the h nu divided by the kT, and that gives you a different set of Gaunt factors. But essentially, what I wanted to introduce to you, as this is a very introductory school, is the fact that if you have charged ionized plasma, and electrons and ions are moving about and interacting with one another, then there will be emission from such a system, mainly due to the fact that the electrons' trajectories will be modified due to the presence of the ions. And that emission can be understood by in a more mathematical way by finding out the dipole moment of the interaction and taking the Fourier transform of it to get the energy spectrum. And the energy spectrum for a single particle and for the other particles is also similar, except for the Gaunt factor, is proportional to the Ne times Ni, and then a Gaunt factor. The Gaunt factor is logarithmic in nature, which depends on some approximate estimates of the maximum and minimum impact parameter. The maximum impact parameter is related to the frequency at which you're observing, and the minimum impact parameter comes from other arguments by comparing the energies. Okay, so before I get out of Bremsstrahlung, I also wanted to introduce another concept. So what we have been discussing so far is emission due to Bremsstrahlung. That is emission due to the electron-ion interaction. You can also have absorption due to Bremsstrahlung. Why is that? Now, assume that this is a thermal system, and if this thermal system is in equilibrium with a black body distribution, any black body distribution function at that particular temperature, then the Kirchhoff's law applies. Now, the important to note that we are not assuming that the incoming radiation that is interacting with the Bremsstrahlung emitting plasma at any given point of time is indeed the black body radiation. This is a fundamental relation. So if the thermal plasma that is emitting Bremsstrahlung, if it is able to be in equilibrium with a black body radiation, then this relation holds. So then we have for the black body radiation and for the thermal plasma, since the thermal plasma is defined by a characteristic temperature, and the black body, and if it is in equilibrium with the black body function, then the black body radiation field will also be defined by that particular temperature. So in that case, the emission coefficient is related to the absorption coefficient in this way. So again, this is a fundamental property of the particular system. This has nothing to do whether the incident radiation is actually black body. This should not be mistaken. That's what I'm trying to say. So if you know the emission coefficient, which we just derived, then you can also know what is the absorption coefficient of the system simply using the Kirchhoff's relation. So the emission coefficient is this. The absorption coefficient, by the simple argument, would be the black body function, the emission coefficient divided by the black body function. Okay, so you have the full expression here. We take this expression for different ranges of energies and kT, and that's not relevant right now. But what I wanted to impress upon you is you can also have absorption by the thermal plasma, and that is also called free absorption or inverse Bremsstrahlung. And there's a very nice example of this. This is from one of our papers, where we do simulations of, say, jets going through a randomly distributed interstellar medium. So this is one of the slices of our simulation. And the jet is assumed to be constituted of relativistic electrons giving out synchrotron emission, which we discussed in the previous lecture. So there will be synchrotron emission coming from the middle of the jet. But this synchrotron emission, once it is passing through this dense ionized plasma surrounding the jet, it can get absorbed due to free absorption. Again, the reason I'm giving this example is the fact that this thermal ionized plasma surrounding the jet, so this is a density distribution. All these clumps are, say, clouds of ionized plasma that is surrounding the jet as the jet is trying to break through the central region or the core region of the galaxy. The distances are in kiloparsecs. All of these small, those blobs of gas will start absorbing the synchrotron emission. So you have an incident non-thermal emission that is getting absorbed due to the free absorption process of the thermal plasma. And what we simulated was the fact that the spectrum would decrease in this way. So if you have an initial power law at some beyond after a threshold frequency or below a threshold frequency, the synchrotron emission starts getting absorbed and then has a downturn like this. What we can also keep in mind is synchrotron emission can also be absorbed by the synchrotron emitting particles themselves. That is called synchrotron self-absorption. I did not discuss this in my lectures, but because this is a bit more advanced, it requires a bit more steps to go there. But you can understand this concept that the synchrotron emission can also be self-absorbed by the particles that are emitting the synchrotron field. And the spectrum for such a case in the absorbed region is proportional to nu to the power 5 by 2. 5 by 2 is here. So this or the spectrum is 2.5. So there's some interesting debate in the literature now that if it is synchrotron self-absorption, the spectrum should be 2.5, but in actual observed systems, many of the times the spectrum is actually 2.5. So that means it is synchrotron self-absorption, but many of the times the spectrum is steeper than 2.5. So the synchrotron self-absorption, which was earlier considered to be the main primary process by which the radio spectrum becomes modified at such lower frequencies, there has been some doubt since the 1990s that the Bremsstrahlung absorption by the intervening gas can also be the contributing factor in decrease of the spectrum at lower frequencies. Again, this is a matter of more debate in the literature, and I don't want to explain it, but I want to show that there can be absorption processes, and the Bremsstrahlung emission is a nice way of how you can identify the absorption coefficient using Kirchhoff's law. So this is an example, and where do we see Bremsstrahlung emission? We see Bremsstrahlung emission from any place which has a hot ionized plasma. Okay, one of the most common examples of Bremsstrahlung emission, for example, are in clusters of galaxies, because the clusters of galaxies have a large reservoir of gas at a very high temperature, temperatures of almost 1,000,000 Kelvin or so. And you can this big ball of gas starts glowing in X-rays, because at that temperature, the peak of the spectrum will be in the X-rays. And this is the example of it. So this pink distribution is of that you see here is due to the gas that is emitting Bremsstrahlung emission. This is a Chandra image of the coma cluster, and this is a nice example of it. You can also see whether Bremsstrahlung absorption can happen or not by using the previous arguments that I said. Okay, so I will briefly touch upon scattering in the next few slides. I just wanted to pause here and see if there are any questions. Okay, I don't see any raised hands. I can understand this is starting to get a bit more advanced and technical, so the questions are slowly drying up, but that is fine. I hope you can take away some of the key takeaway messages, because it is not expected for you to understand, especially for the younger audience, to understand everything in such a short span of time. But the flavors of the different things is better if you can have a takeaway. So Soham Bose asks in the chat, what is the difference between free and self-absorption? So free absorption is when you have an incident radiation field coming through the thermal plasma, and that is getting absorbed. You can also have Bremsstrahlung emission by the given thermal plasma also getting absorbed by itself. So self-absorption is when the particular emitting region that is emitting the radiation, that itself is absorbing the radiation. What I talked about is synchrotron self-absorption and free absorption. So synchrotron self-absorption is when the synchrotron emitting plasma itself is absorbing the synchrotron field. So there is some absorption coefficient associated with the synchrotron plasma. And if you put a ray or put a square through it, a line through it, and perform the radiative transfer, the synchrotron emission coming from one part of the ray as it is proceeding through the synchrotron emitting plasma will get absorbed. Similarly, if you put a ray through the Bremsstrahlung emitting region, that also can get absorbed, but that depends on the frequency at which you're observing it. Is Dr. Sarangi asks, is the colors of the Horsehead Nebula should also be due to Bremsstrahlung emission? Yes, Horsehead Nebula, well, it's a bit difficult to say in that way, because a nebula will also have considerable amount of contribution from background stars that are forming in that region. So a good amount of emission is due to the photoionization from the stars that is passing through the gas, and part of this photoionized gas is being absorbed by the dust and cold gas which will then be re-emitted in infrared and other frequencies. So I don't think Horsehead Nebula is a very good example of Bremsstrahlung. But of course, there can be ionized regions close to, say, the photonization zones, and that will still have some contribution to the due to Bremsstrahlung emission. Uh, Aarti asked about reference books and reference textbooks I have already mentioned. Pushti Shimankar, please ask your question if you can unmute yourself.
Hello, sir. Sir, in the PPT of brainstorming multiple in plasma, I have one doubt from that, sir.
Okay, let me try to go there.
Yes, sir.
This one, okay.
Yes, sir. So, for the classical case, one line is told that this implies weak scattering breaks bayon and particle paths if not in a straight line. Sir, I couldn't understand this words.
Yeah, so in the classical case, the B minimum is actually larger. Okay, so if I go to this particular graphical presentation, so you see the basic thing is the electron's trajectory has a change due to the ion. Now, in the classical case, what we assume is this change in trajectory is very small. So essentially, the electron almost continues along the same path with a very slight. So I am enhancing the deviation here just for better understanding. But for the classical case, we'll assume the electron has very small deviation and almost goes along the same path. Okay, so the change in the vector is very small. If the change in the vector is substantial, then we go to the quantum description. Okay, does that make it answer this question? I guess you can't unmute again. So I hope it addressed the question. Okay, so I think I'll pause the Q&A here and then go to the next few slides. I just have about 15 minutes left. Again, scattering is a more advanced topic. It usually takes again several lectures to go through in detail. But what I wanted to impress upon you is two of the different mechanisms by which we consider the impact of scattering. So, firstly, we will consider a non-relativistic interaction of an incident electromagnetic radiation field with a electron, with a charged particle. So in this way, what we'll assume is there is a incident electric field here, or incident radiation field with a, of course, which will also have the electric field, and the charged particle would be oscillating as a in response to this oscillating electric field. So then what we will do is we will find out again what is the dipole moment, and then we would try to compute the spectrum. That's again the steps to follow to get the total emission is same. It's just that the nature of the particle trajectories and the particle motions are different, so the acceleration vectors are different for different scenarios, and that is why you have to compute them separately to get the total acceleration vector. Once you get the acceleration vector, you are done. You can find out the spectrum or the power emitted. So in this case, what we assume is the particle acceleration vector looks like this. Again, it will form a dipole moment where the particle is or the electron is oscillating. And once you identify the acceleration vector due to the dipole moment, which will be something like this, you can use the standard arguments due to power radiated per unit solid angle of a dipole moment. Again, this is not exactly discussed, but you have to take my word for it. Which is dp d omega will look something like this. Again, look at how you recover the dipole formula expression of the power emitted. So this will be the expression of the Poynting flux, and this is the scattering cross section, or d sigma d omega, is defined as the power per unit solid angle divided by the Poynting flux. Again, this is just a definition. So this is the differential scattering cross section, which shows you that for a given solid angle or a given direction, what is the scattering cross section. So this is d sigma d omega. To find the total scattering cross section, we integrate over all the solid angles and we get this relation. So this simple, I went very fast through it, but essentially there is nothing more to describe here except the fact that you are considering a non-relativistic interaction of a particle with an incident electromagnetic field. Once the electromagnetic field comes, the particle will re-radiate because it is the incident energy, because it is oscillating as a response to the electric field, with response to the incident electromagnetic field. And the particle will radiate its energy in all different directions. So you have an incident field, incident radiation coming in one direction, but the particle will radiate in all sorts of directions given by this dipole nature of the radiation field, since sine squared theta. This dipole and this dipole moment are different, by the way. So let's say it will emit due to the sine squared theta in a sine squared theta form, not to avoid confusion. And the total scattering cross section of this is given in this way, which is the very basic and standard expression, which is called the Thomson scattering. So if you have an incident radiation field interacting with an electron, the Thomson scattering is a first kind of thing that one will consider. Since these are non-relativistic, we'll ignore any other relativistic effects. If you have to include relativistic effects, then this simple expression of the Thomson scattering cross-section gets modified, and one has to consider what is called the Klein-Nishina cross-section. I will not go into the details of that. So that is called Thomson scattering, which is a non-relativistic interaction. Now, let us try to understand. So here, since it's all non-relativistic, we consider the incident electromagnetic field as a wave, and the particle was responding to that wave and then oscillating and then giving out radiation. So that's one form of scattering. Other form of scattering is when the particles are moving at very high velocities. Then it becomes interesting because now, because of the relativistic nature of this of the incident rate of the motion of the particles, we have to consider interaction between the photons and the particles separately in the momentum phase space. So this is called Compton scattering, where we have an incident radiation field with some photons associated with it due to its energy that comes and interacts with the particle, and then the photon leaves and the particle also gains some energy and goes in a different direction. So to understand this interaction, what we do is we first go to the rest frame of the particle. So initially we consider the particle to be at rest. I'll show you exactly what happens when we go to the lab frame. It becomes very interesting. So then we have the incident radiation field with a photon of energy E h nu coming and interacting with the particle. Then the photon leaves with some other energy E1, and the particle goes in a different direction. So now you have the initial momentum flow vector and the final momentum flow vector. Just apply basic conservation of momentum, and you find that you'll get an expression of what the outgoing radiation would be in terms of the incoming radiation and the angle of interaction, which is the angle at which the photon is scattered with respect to the initial direction of the photon. So the expression looks something like this, which is E1 prime. So all are prime because we are working in the rest frame of the electron. E1 prime is related to the incident photon epsilon prime divided by 1 plus this factor plus 1 plus multiplied by 1 minus cos theta prime. Now note that if this factor is small, which is if the incident energy is much smaller than the rest mass energy of the electron. So that is if x, which is epsilon prime divided by mc square, is less than 1, then the scattered energy of the scattered photon is the same as the energy of the incident photon. So what the photon essentially experienced was just a change in direction. And this is called elastic scattering in the rest frame of the electron. So in most of the cases, and in many of the cases, we deal with photons that do not go all the way up to 511 keV. 511 keV is the rest mass energy of the electron. So we do not go to high X-ray energies or gamma rays. In such scenarios where we are less energetic with respect to the rest mass of the electron, the scattering is usually considered to be elastic scattering in the rest frame of the electron. Now we'll again go through these arguments, but in terms of the lab frame. Again, what this involves is a series of special relativistic transformations. I will not go into the details of it because this is just mathematical in nature. But what is important to note is what you get out of this expressions here. So let me just try to simplify it. So in the lab frame, or in a frame in which the electron is itself moving, suppose the electron's trajectory is in this way and the photon's trajectory is in this way. So what we do is we go to the frame of the electron, compute the scattering in the frame of the electron, and come back to the frame to the lab frame to find out what is the final expression of the energies. Once you do that, you will get something like this. So this is the final expression. So even if it is elastic scattering in the rest frame of the electron, once you do a frame transformation from the electron's rest frame back to the lab frame, you will find that although it is conserved energy in the electron's frame, the final energy of the scattered photon is related to the initial energy in the lab frame in this way. This is the expression to note. It's just a series of transformations. So what we do is go from this. If epsilon is the incident energy, you find epsilon prime, which is the incident energy in the electron rest frame. You consider the fact that the final energy due to elastic collision is again epsilon 1 prime, and then do a deboost to the lab frame to get the epsilon 1 from epsilon 1 prime. And you have a series of expressions of the cos theta, etc. If you put everything here and use such identities, you get this relation, which is if you have the incident angle theta and the outgoing angle theta 1, the final energy of the scattered photon is related to the initial energy is in 1 minus beta cos theta and 1 minus beta cos theta 1. Now, there are a few things that you can find out, few sort of limiting cases. One is a head-on collision, where the photon and electron approach each other directly. So in that case, theta equals to pi and theta 1 is almost equal to 0. Okay, so you have to take my word for it, but one can show this is the case. So if that is the case, then you have the maximum energy of the scattered photon is related to its initial energy in this way. So what you can see is although in the electron's rest frame, the collision was elastic, that is the incident photon's energy did not change. Once you transform back to the lab frame, you see that the scattered photon's energy has increased by 4 gamma squared. So this is the maximum energy that the scattered photon can get, and that is called a head-on collision. So in this case, what happens is what is a head-on collision? Where the photon and electron are interacting with one another, and then the photon is reflected along the path of the electron itself. So initially the directions are pi because they are opposite directed velocities, and after that they are directed in the along the path of motion of the electron. So this is the maximum energy a photon can get out of that electron, which is 4 gamma squared epsilon. The other limiting case is the tail-on collision, where the photon strikes the electron from behind and then is reflected in the opposite direction. Okay, so initially then theta equals 0 because the photon and electron are moving in the same direction. But after the interaction, the theta is pi because the photon and electron are separating out and going in opposite directions. Again, you put those factors in here, you get that the photon will lose energy. So the electron is getting boosted, and the photon will lose energy by epsilon by 4 gamma squared. So one can remember that this is the nature of the of scattering due to relativistic motions with due to interaction with the radiation field with a relativistically moving particle. That although it is an elastic scattering occurs when the energy of the incident photon is less than the rest mass energy of the electron in the electron's lab frame, in the electron's rest frame. And in the elastic scattering, the photon can gain energy to a maximum value of 4 gamma square, depending on how the interaction was, if the electron and photon were having a head-on collision. And if there's a tail-on collision, then the electron can lose energy. So in this way, you can boost. So suppose a low energy photon goes and strikes a highly energetic electron, that photon will be upscattered to higher frequencies. On the other hand, there can also be downscattering. So that depends on the relative direction of the photon and whether there is more upscattering or downscattering. Will define what your final spectrum will be. So in this way, so upscattering of photon is very naturally observed. For example, in accretion disks, or for example, as I had given this example earlier as well, we have an accretion disk where thermal plasma is falling inside, is rotating around and heating up and emitting thermal photons. This thermal photons that goes and interacts with a hot corona of hot electrons surrounding this accretion disk. Some of these photons will be upscattered to higher frequencies, and that will go to the observer. So essentially, the observer will see two distinct components of spectrum. One due to softer photons or low energy photons coming from the accretion disk, which are thermal in nature, and one which are getting upscattered by this cloud of electrons on top of the accretion disk. And that usually forms a power law distribution. And those are the Thomson upscattered electrons. So I think I have finished my intended slides. I will wait for any questions on this topic. So if you have any questions, please raise your hand. I can quickly check if there are any questions on the Google Sheet in the meantime. Okay, so Najia KM asks in the Google Sheet that what is the difference between brightness temperature and black body temperature? Okay, that is related to the definition of brightness temperature. Let me find out where I had done it. Was it here? Yes, I think I discussed it over here. Yeah. So brightness temperature is when we, again, let me explain what is the definition of brightness temperature. You take the incident intensity of a given radiation field. What you have is a measure of the intensity, that is a power per unit solid angle per unit frequency per unit time. You usually find out by measuring the flux that you're receiving in a given radiation field. So you see you have a flux of radiation coming towards you. You identify some intensity associated with that flux. And then you use this formula to ascribe a temperature to that to that radiation field, but not to the radiation field, but temperature to the object that is giving out the radiation. Now, if the radiation is due to a thermal body, then and if the Rayleigh-Jeans limit applies, that so that the intensity coming out of the thermal body is a black body in nature and in the Rayleigh-Jeans limit, then that temperature that you get from the flux that you have received in the detector would be proportional to the black body temperature, except for a factor. However, if the object that is emitting that radiation is not a black body, but is of non-thermal nature, then the temperature you ascribe to it has no meaning. It has no physical meaning. It is empirical in nature, and that is called then. But in any case, that is a brightness temperature. So essentially, what you do is you obtain the flux in a detector. You find what is the brightness temperature using this formula. If it's a black body, then the brightness temperature is the same as the black body temperature. If it's a non-thermal object, then the brightness temperature has no physical meaning. I hope I have repeated this several times. I hope it is clear now. Shubhata Sarangi says, very interesting processes. Thank you. Thank you for listening, Dr. Sarangi. Soham Bose asks, why is synchrotron absorption advantageous for radio galaxies? Radio galaxies have no advantage or disadvantage in having synchrotron emission or absorption. They don't care. It's a part of the physical process. So I don't exactly understand what do you mean by advantageous for radio galaxies. Maybe Sham, if you want to unmute yourself, maybe I'm not getting uh, the the sense of the question. Soham Bose, if you can unmute and ask the question directly that you've written in the chat to me. Soham Bose is not unmuting, but I yes, Soham, if you can please unmute and then ask. If your audio is not working, then you I cannot really understand that question. Ajay Kumar asks, Thomson scattering is not in Ribicki. Which reference book to refer to that? Ajay, Thomson scattering is in Ribicki. It may not be there in the chapters related to Compton scattering, but it is certainly there in the earlier chapters. I exactly forgot the number of the chapter, but it is related to the chapter where they discuss radiation from moving charges. In that section, there is a derivation of Thomson scattering. Okay, Soham, your audio is not working. So, advantage. Okay, let me go to this slide. Perhaps what you're saying is absorption is advantageous to radio galaxies. Are you trying to say this line, a good application is for radio galaxies? So what I tried to mean here was it is not advantageous to the evolution of radio galaxies or something. What I meant here was these processes are well applied while inferring the nature of the radiation from radio galaxies. So when we observe a spectrum from radio galaxies, again, maybe I'll put my slide in full. So forget the absorbing part. We usually have a power law distribution like this. But if you have any absorption process, especially at the lower frequencies, then the power law decreases like this. And this kind of inversion in the spectrum is usually seen for young radio galaxies. The kind of radio galaxies they occur for are called the compact steep spectrum, CSS, or gigahertz peak spectrum, GPS. Why gigahertz peak spectrum? Because if you can see the frequency here, that is almost gigahertz. So below the gigahertz, it starts decreasing again. So GPS and CSS sources are usually young, compact radio galaxies, so the jet sizes are about a few kiloparsec, where the jet is still evolving and growing out of the galaxy. It has not grown to very large scales of hundreds of kiloparsecs as we know them to exist. And for such cases, we do see the spectrum appear in this form. And what I meant was a good application of these absorption processes to interpret the spectrum is for radio galaxies. Okay. Apra asks, sir, could you explain the means of thermal equilibrium of plasma ions and black body radiation? There is no means of equilibrium. What I meant was a theoretical construct where suppose the thermal plasma is in equilibrium with some radiation field. And if that is the case, the radiation field becomes a black body radiation field. Okay. So in that case, the absorption coefficient and the emission coefficient are related to one another by the black body function because of the Kirchhoff's law. Okay, I don't see any raised hands, neither any further questions on the chat. You're welcome, Akura. And nothing on the Google slide as well. Let me check. Yes, nothing on the Google slide as well. So I will end my lecture series here. Thank you all for listening. I know this was very rushed. I had to gloss over many different things which are a bit more complex. But what I hope you have taken, the takeaway message from this, it would be that you have understood some of the glimpses of the radiative processes that take place. And I tried to highlight some of the examples where they apply. Of course, these are vast subject areas where you have to focus on and read up on. So I will share the notes now with Santosh. I will also append the initial section of the books with the reference to Longuet. And if you have other questions, you can write in the Google form. I'll try to address them on Slack.